My name is Karin Habshi, and I'm going to give you the GNE33 engineering analysis for this summer. It's an easy course, just you should follow up because you have several methods, several numerical methods that you will learn, and you should know how to use them on your own. Okay, so just you need to do a lot of practice, but as it's not a difficult course, just it needs some practice. Okay, for this reason, if you go to Blackboard, I already divided for you the course into several parts. You have the course syllabus. The course material will include all slides that we will do together. In the course material, we will go over examples during explaining the material. And in addition, I will post for you assignments to practice on each chapter we will do together. Okay, so please try to, because especially in this semester in summer, the time is very short. So we have 3 exams in this course. So maybe in 10 days we will have the first exam. So please try to follow up with the course on daily basis. And in links, you will have the different links that we will use in the course. We have until now the Zoom link. I will post also for you WebEx link for which we will use for proctoring during exams. And also I will post for you a playlist, a YouTube playlist link, where I will post all recorded sessions, so you can go to it whenever if you cannot attend the class, for example, for a certain time, or if you want to review again the classes, you will have them in the YouTube playlist link. Now, I will introduce the syllabus of the course, and then we will start by an introduction chapter today. So first, this course, you will use it a lot in engineering. It will introduce for you numerical techniques that you can use to solve engineering or any physical problems, even not physical problem, any mathematical problem. Okay, so you know in any field you have equations and you should solve equations. Sometimes you don't have an exact solution, so you are forced to go to numerical techniques. In this course, we will go over several numerical techniques. You will learn their advantages and disadvantages and know what are the limitations, when I can use them, etc. So this course will compare and contrast various numerical analysis techniques in addition to definition of error. What is the error definition? What is an acceptable error, for example? You will see the stability of a solution, the machine precision concept. So for example, you will see that what is the precision of a calculator, what is the precision of a computer, what is the error that we can have when we use these equipments, etc. And we will see the inexactness of computational approximations. What is a floating point arithmetic? We will study conversions of a solution. We will learn iterative solutions for finding the roots. We will learn curve fitting techniques. So if you have several points, how you can get a certain function in a way to represent these points. We will go over function approximation and numerical differentiation and integration, in addition to how to use initial value problem for differential equations and finite differences. So we will go over all of these in this course. Now, once we finish this course, you will be able to understand the most common numerical methods used in engineering analysis. And also, we will develop a lot of techniques that can be implemented in MATLAB. Okay, so all methods we will learn together, you can easily program them and use these programs to find the solution you want. Second, we will learn about numerical accuracy, which estimates the amount of error inherent in different numerical methods. We will see what is numerical efficiency, which will assess the efficiency of a selected numerical method when more than one option is available to solve a certain class of problem. So we will learn in this course several methods, and at the end you will know which method is more convenient for any problem you face. Finally, we will go over numerical stability to understand the convergence properties and limitations of different numerical methods. You have methods that always converge, while others that can give you divergent results. So we will learn which methods will always converge and which method might not converge. But the methods that might not converge in general are characterized by they are very fast. This is why we like them. They have the advantage of being fast. So even if we have a risk to not converge, we go for them because they are much faster than other methods that can converge, that will converge surely, but might need more time. So we will see the different methods and we will see in which cases we apply each of these methods. Now, for the book of the course, for the book that you will use in this course, you can use, it is the Applied Numerical Methods with MATLAB for Engineers and Scientists. The author is Stephen Chapra. And you can use the third or fourth edition. You can download it easily from the internet, this edition. It's a very nice book. It is very helpful. You can read in the book in parallel with the course material because it explains in detail everything. The slides are more than enough. So if you understand well the slides and what we explain together, no need to read in the book, but it is nice. It's a nice book. It can be helpful for you. Now, concerning the grade distribution in the course, you will have 3 exams and 1 final. And as I told you, because the time is very short, so expect each week or each 10 days. Now, for the first exam, I expect within 10 days we will have it. And after this, maybe after 1 week, the second, and after 1 week, the third, because the time is limited. So, and the grade distribution is in your favor. So the lowest will be 15% for the lowest exam, the second 25%, and the third 30%. And for the final, it will be on 30%. And as usual, you know the criteria of grading. So we follow this table for grading criteria. In case you have any questions, we can organize an office hour whenever you want. We can do a live session on Zoom, or if you want, you can ask me on WhatsApp directly. I don't have any problem. And also, you can send me an email. So feel free to use the method you like. Just you tell me. I prefer by WhatsApp because I can directly say, I check my email every day, but on WhatsApp, I will directly see that you are contacting me. So I prefer WhatsApp if it's fine for you. And this is my email. Okay. And of course, in class, whenever you have a question, if you don't understand anything, you can stop me and ask. Okay. So this is mainly the syllabus, what we want to know from the syllabus. Now we will introduce the course. So chapter 1 is about mathematical modeling and numerical methods and problem solving. So the course objectives is to develop the ability to solve engineering problems numerically and to evaluate numerical solution methods, knowing the advantages and limitations of numerical methods. So at the end of this course, we will be able to select the appropriate method, numerical method, to solve a certain problem. As we said, it can be an engineering problem, it can be any problem involving equations. So whenever we have to do a mathematical modeling, we have 4 steps to follow. First, we should develop an approximate, usually ideal setting to study the most important aspect. What we mean by this, that you know that in any problem, you might have a lot of secondary effects. But if you want to model all of these, you will have a very complex mathematical model. This is why, in general, when we talk about a mathematical model, we neglect secondary effects, for example, as the surrounding light, the noise, etc. Okay? While when you perform experimentation, all of these will be taken into account because it's a real practice. You are doing experiments. Now, in general, in research, what do? Whenever we develop a mathematical model to validate it, to say that I did a lot of assumptions, but to make sure that my assumptions will not give me results that are very far from reality, what we do in general that once we develop a mathematical model, we do a certain experiment, okay, and we use same inputs to make sure that the mathematical model is able of predicting the experimental results. And once we validate it, you can just do 1-2 experiments. Once you validate your model, then you can use it for a parametric study, and you can change as many parameters as you want. Because you know that it's hard experimentally to do a parametric study. What I mean by parametric study, I change one parameter. Okay, so I can have several parameters. I fixed all other and I change one, and I will see their effect. So if I want to do everything experimentally, it will take a lot of time and it will cost a lot. This is why mathematical modeling is very important. It will save time and it will save money. So we should formulate governing equations for a problem by taking certain assumptions, and then we will solve these equations analytically using numerical methods. And in general, the majority of engineering problems does not have an exact solution. If you have taken the fluid course, you have seen Navier-Stokes equations. They are very complicated, and in general, we solve them using computational fluid dynamics, which is CFD. This is CFD. What we do, we transform these equations into algebraic equations that can be solved numerically. So a solution may be used in a variety of similar applications. So as you will see here in this course, we'll develop general numerical techniques that will be applicable in a variety of applications. For example, now in this introduction, we will just take a simple example and we will see how we can use numerical methods to solve. It is the problem of a bungee jump. So let us say you are asked to predict the velocity of a bungee jumper as a function of time during the free fall part of the jump. You know that when you do a jump, you have several stages. First, you have a free fall, and in next stage, the cord will allow you, will be in tension, okay, and it will have a force on you in addition to gravity and resistance of air. But in a first step, you just have the free fall since your cord is not yet in tension. And during free fall, you are just subjected to your weight and to the resistance of it. So for example, in such problem, our purpose can be to determine the strength and length of the cord based on the jumper's weight. So the cord will vary from jumper to jumper based on their size. So in order to do any modeling in this case, first we should examine the free fall to know what is the final velocity in the free fall before the cord will be in tension and will do a certain force on the jumper to hold him. Okay. And similar analysis can be done for parachutists in free fall, for rainfall, for ballistic trajectories. So what we will do here can be applied also in other similar applications. So to start with, I will do the analysis of a real-life problem, which is bungee jumper. And I want to develop a simple mathematical model that will predict the behavior of the jumper. So first, I should do some approximation and assumptions. For example, here, I can neglect the weight of the rope. I can neglect sideways wind, and I can neglect motion of the jumper. I will treat it as a particle. So if you have taken the dynamics course, you know what is the difference between a particle and a rigid body. And I will consider that, of course, the jumper maybe will move his hands or will have relative motion between the body parts, but I will neglect this to simplify the modeling. So now, the simplest approach I can go over is to apply the Newton's second law and just to consider the main forces acting on my on my bungee jumper. Okay, so these forces are the weight and the resistance of air. So I can just apply Newton's law. I can say that if I apply sum of forces on my jumper, I have the downward weight and I have the resistance of air, which is an upward force. That you know in general that this force is proportional to the square of velocity. So now I will replace in my equation. My objective is to determine the terminal velocity of the bungee jumper at the end of the free fall. Okay, and you know that acceleration is defined as the derivative of velocity with respect to time. So now, if I replace in my equation, I will get the following. My equation is m times dv by dt. So this is the acceleration term. I transformed a into a derivative. And you will see that numerical methods will offer several options to compute the derivatives. So mdv by dt is equal to the downward force of gravity minus the air resistance force. Now, the weight is given by m times g, while the resistance force is from fluid mechanics is the drag coefficient times v squared. Now, also here it can be very complex, and we can, in general, CD is not a constant. CD vary with the velocity. Okay, so you imagine that it will become very complex if I want to take CD variable, because I will have to take a new value for CD for each step because the velocity is changing, so CD is changing. Now, for the time being, we will assume that CD is constant. We will see after what to do if CD is variable. Okay, so in future chapters, you will learn techniques to solve this equation in case CD is not a constant. So, in case CD is constant, I will obtain this differential equation, and I can solve it analytically. So you have seen, if you have taken differential equation course, you know that this form have an exact solution. Okay, but what is the condition? The condition is that CD is constant. If CD is function of V, I cannot have an exact solution. Okay, then I am forced to solve numerically. So in order to solve this equation, I just need to know an initial condition. In this course, you are not responsible of knowing the exact solution. Okay, so don't worry about it. Even if you didn't take already the differential equation course, it's fine. Okay, you don't have to know how to solve analytically an equation. We will give you the equation, and just you should know how to solve it numerically. So just here, for your information, any differential equation needs a boundary condition. Knowing the boundary condition, I can know the exact solution in this case, because it is a common differential equation with constant coefficients. So now here, for me, it's fine. I can solve it analytically. Okay, and this will help us now because we know the exact solution. This will help us when we develop numerical methods to compare between numerical solution we get and the exact solution. But in general, why we use numerical solution? Because we don't have the exact solution. So now, just in this example, we gave you the exact value to compare, just for comparison, to develop techniques for numerical solution, how we can approach in a better way the exact solution. And in case CD was variable, I don't have an exact solution, so also we will develop corresponding numerical techniques. And after having a certain experience with numerical techniques, we can come up with methods that can predict accurately the final solution. Any question until here? Please, if you don't understand anything, stop me and ask. So now we have this ordinary differential equation. We can solve it numerically in an easy way. In order to solve it numerically, we should know how to compute the derivative. Okay, how to compute the derivative. You have several schemes, several methods to compute a derivative. You know that analytically, a derivative is defined as dv by dt is the limit when delta t tends to 0 of delta V over delta T. So this is analytical. When we want to use the numerics, we will not go to 0. Okay, we will use a certain finite number. Okay, but it will not be as close as 0, because you know that when delta T tends to 0, this becomes indeterminate. So what we will do here, we will take a certain time step delta T. And of course, smaller is delta T, better is the approximation. So you can say, I want to take delta T 1 second, I want to take it 0.1 second. And as predicted, smaller is delta T, better will be your approximation, because you will get values that are very close to the real value. So just here, the difference between the analytical solution and the numerical solution is that we don't take delta T to go to 0. We will take it as a number different than 0. But as we approach 0, our solution will be more exact. Now, the question is how to compute numerically this term. Because one might tell me, if I have a function, let's say a point I, this point is surrounded by other points. I have points after it, and I have points before it. So if I want to assess what is the derivative, I have several possibilities. When I want to talk about delta V over delta T, you can tell me I want to compute delta V from these 2 points. Then I will say that delta V is V at I minus V at I minus 1 over T at I minus Ti minus 1. You can also tell me, no, I want to take point I with the point that is coming after it. So I want to take I with I plus 1. Then it will be, delta V will be Vi plus 1 minus Vi over Ti plus 1 minus Ti. Another approach also, you can say I want to take into consideration the point after I and before I. And sometimes in some methods, they take 2 points after and 2 points before. So they say in this way, I can have more accurately a representation of the derivative. So you have several methods when assessing delta V over delta T. And we will see them together today. And we can compare their effectiveness by doing appropriate calculation. So to start with, so delta V over delta T equal Ti plus 1 minus Vti over Ti plus 1 minus Ti. This is the forward method, and also it's referred as Euler's method. Okay. Now we will see the different possibilities of writing the derivative term. So one possibility is the forward difference method. When we say forward difference, this means that we take the point after. This is why it's called forward. When you compute the derivative using the point before, it's called backward difference. And when you take the point before and after, it's called centered difference. Okay. In general, this method is fine. Why? Because in general, let's say at t equals 0, you know your condition. So knowing condition at t equals 0, I can know, if you take, for example, a time step of 1 second, knowing at t equals 0 what is the condition, you can compute what will happen at t equals 1, which is the point just after t0, etc. Once you find at t equal 1, you can conclude at t equal 2, and it is an iterative solution. So you always need just one boundary condition to start from. And if you replace dv by dt by the forward form of derivation, which is vi plus 1 minus vi over ti plus 1 minus ti, then here you will take g minus cdm times the velocity at point I squared. So if you know, for example, at t equals 0, what is v0? Let's say v0 equals to 0. Then when you want to compute v at 1, for example here, if you want to compute v at 1 seconds, you say v1 minus V0 over T1 minus T0. In general, we take a certain constant time step. And if you choose to take delta T equal to 1, so delta T here will always be 1 second. So this is equal to the time step, delta T. For example, here we consider it equal to 1. Equals to, from the other side, you have G minus CD over M, V squared. Now, you will replace here by the velocity at point 0. So as you can see, you can predict V at point 1 function of V at point 0. So here we rearrange terms to take all VI terms to the other side. And in this way, we got VI plus 1 function of VI and delta T. Okay, so here also always VI is at the previous point, and now you want to assess VI plus. So in this way, you can compute the value by iterative solution. You can get first V1, from V1 you get V2, and you repeat this procedure as long as you want. So you can cover any time you want. Now, so what we did here, in this numerical method, we discretized time along the t-axis, and we considered that for each ti, we have a certain corresponding velocity vi. So this is a discrete. Why we call it discrete? Because we know just points of the function. We don't know what is the equation, but we can find just points. And at the end, more we find points, then we can interpolate. And in this course, we'll know how to interpolate between points. So let's say you got delta t, you use delta t equal 1, for example. And let's say you are interested in knowing what will be the value in between here. So let's say this is, for example, 2 seconds, and this is 3, for example. You are interested to know what is the velocity at 2.5. Then we will see in this course what are the techniques that can be used for interpolation between 2 points. And more delta t is smaller, you will have more points, and then you can have a better approximation. So here, if you want to draw a curve joining the point, you can draw it, but more you have points, more your curve will be accurate. Okay, so let's say because if you have these 2 points that are very far from each other, you can join them in several ways. You can join them straight in a straight line. You can join them in a curve like this. So you have several possibilities. This is why the smaller is your interval, then your curve will be, you can see your curve in an easier way, and your interpolation will be more accurate. Now, as we talked about, the derivative can be computed numerically in several ways. The first method is the one used in Euler method. Yes, Muhammad, we should know. We should set delta t. Delta t, you set it. You can take any delta t you want. Okay? So you can put it 1 second, 0.1. You are free to choose delta t. And you need one time boundary condition, of course. But for delta t, you set it. It's not given. It can be given for you if they ask you use delta t equal to 1, for example. But also you can change it. You can use several delta t. It's not a fixed value, but the boundary condition is fixed. Okay?
Okay, thank you.
So the first way is for derivative is the forward difference method. And as we introduced it, just we have to take the point after. So if I have, let's say, v at ti, and I want to predict the derivative at ti, I will take the point just after it. So for the point after it, I have vi plus 1. So this is vi plus 1. And this is vi. So using the forward method, I can define the derivative at t equal ti as vti plus 1 minus vti over ti plus 1 minus ti. And this will give me a numerical computation of the derivative at t equal ti. This is called the forward difference derivative, or first derivative. Now, another method, as we discussed together, is the centered difference for first derivative. So in the centered difference method, we take into account the point before ti and the point after it. So it's ti minus 1 and ti plus 1. And in this case, the interval here will be 2 times delta t. Okay? Because between ti and ti plus 1, you have interval delta t. And between ti and ti plus 1, you have also delta t. So in total, in this case, when you divide, you will have to divide by 2 times delta t. And it is vi plus 1 minus vi minus 1 over ti plus 1 minus ti minus 1. So this will be 2 delta t. Just I have one question. Let me see your questions. Yes, Karen, dv by dt is the acceleration. And when we wrote Newton's second law, we replaced A in sum of forces equal ma. We replaced A by dv by dt. Okay? Muhammad, what do you mean by less accuracy? For what?
Since the interval is greater, بيصير accuracy less.
Yes, ده أكيد. كل ما كبرت delta t, كل ما accuracy less, of course. Smaller is your time step, better is your accuracy, but also higher is the computational time, because you will need, if you choose a smaller, if you select a smaller delta t, in order to cover a certain range of time, you will have to find several points, and this will take time. So you should always compromise between accuracy and computational time.
Oh, okay, thank you.
Okay. Okay. Now, going back to our method, we will try to solve, okay, this problem, which we discussed together. We will try to solve it for a certain set of numbers. So if they gave us the mass, if they gave us, just 1 second, let me clear this. Okay. So let's say they gave us the drag coefficient, the mass, the boundary condition, and they asked us to predict the velocity for a certain interval of time. What do? We will use the forward difference method in this case. So let us say they gave us all what we need, the mass, the drag coefficient, and they fixed delta t to 2 seconds. Okay, and we want to solve in between 0 and 12 seconds. Okay, so first we know that at t equals 0, v equals 0. We know the first point, and we want to compute, since delta t is equal to 2 seconds, then we should find the velocity at 2, at 4, at 6, 8, 10, and 12. So if in case you have delta t equal 2 seconds, you should do 1, 2, 3, 4, 5, 6 calculations. So imagine now that delta t becomes 1. So you should have you should do a double number of calculations. So from 1 to 12. So of course it will be more accurate, but also it will take much more time. Okay, so always, as we said, we should compromise between accuracy and computational time. Time is very important at the end. And of course, accuracy is also important. So we can choose a time step that will give us acceptable results and also that will save time for us. So here to proceed, all we have to do is to start by t equal 2 seconds. we have v at 0 is known, so we replace v0 here, plus g minus cd over m times v squared, so here it's v0 and this step, times 2 minus 0. Now what will change from one step to the other is the following. It's just the velocity. So now you got the velocity at point at 2 seconds. Okay? V at 2 seconds. You will use it in the next step. So now to compute V at 4 seconds, you will just, instead of V0, you will put V2, V at 2 seconds, plus G minus CD over M times V at 2 seconds squared. And delta t is remaining the same, it's 2 seconds. You get now V at 4 seconds, and you iterate. You will repeat the same procedure. So now you will replace V at 4 here and here to get V at 6, etc. In this way, you will get the velocities at different times. Okay, just let me check the questions.